We're done now. It's 9:20.
So we'll go.
Did we finish the thing?
So I said I was going to present on MPI and OpenCL, so let me at least present on OpenCL today, and then I'll probably finish up with MPI on Wednesday and go through the rest of the slides on Wednesday, and then on the following Monday we'll have to do a final special presentation on Meltdown Inspector. No, because then on the 23rd is when you do your presentations.
Yeah. So we'll finish the stuff from last class next time.
Presentations individually.
Okay. All right. First off, I totally took these slides from George.
Thanks, George.
Thank you, George. These are back back in 2012, so these slides are old, but I think they do a good job of explaining the situation, and they've really.
Years? That's ancient.
It is ancient, but in reality, what he's talking about here has only pretty much just exploded even more so. So I think this is a good starting point. So what happened just 2 years ago? You know, again, think in 2012, so this will be 2010. These are the huge top three. Bless you.
Waiting for that all day.
Yeah. Top three supercomputers back in 2010. And one thing you'll notice is while they have a good number of processors, they also have a good number of GPUs. And what's going on is supercomputers are starting to leverage.
Except the Jaguar. It doesn't have any.
Yeah, we don't care about that. I think that's a Chinese machine. Anyways, well, yeah. Basically, even supercomputers are starting to leverage the power of GPUs. So you're starting to have a heterogeneous situation where you have your normal processors, Xeon, aka Intel i7s, but for servers. Opterons, those are AMD's high-end chips. And then you'll start having GPUs on top of it.
Start having GPUs on top.
Yeah. All right. So what relationship? What? Go
Isn't
ahead.
the first one Chinese though? Isn't that
Yeah, they're all Chinese. Yeah, the first.
TIA?
Yeah, that's Chinese. So what relationship can you see between G-flops and power?
Doesn't matter.
How about G-flops, GPU, and power?
Doesn't
Wow.
I guess
The lower of
I don't-
everything gives you the lower of everything.
Well, what's the one that doesn't have a GPU? How much power is that thing
That's a
consume?
lot of
The
power.
most.
So you need to have a GPU.
So GPUs are processors.
But
But the one that has the most power doesn't have the highest G-flops.
It's the number of processors.
So, well, the point. Oh yeah, this one has wow, that's an insane.
That's insane.
That is insane. What's really going on, guys, is that the GPU is able to give you more computational power at lower energy consumption.
You want to mix.
You do want to mix. Yes.
Perfect one.
That's perfect. So how was it? How are GPUs changing computation? The example they go through in this slide is doing simulations, but a very similar slide could be presented for what is it called, bit mining, as well as other types of crypto calculations, right, Jonah?
Yeah. Of course.
So their example here is basically computing the field strength of neighborhood of a molecule. It's very common to do simulations of. Atoms and
I was
molecules.
laughing at what you said.
So you want to be able to do all these in parallel. And what they're trying to point out here is, I don't know why here. Okay, ignore the slide up there. If they were, this is your initial molecule that you have, and they want to basically decide what's the power range between them all. So see how there's little power fields here and there, and blah, blah, blah. On a single core, they say it takes about a minute. On a 16 cores with 16 threads, it's about 2 seconds. Does that make some sense? I think that, yeah, that makes some sense. And then on, well, oh, I'm sorry, yeah. That makes more sense. About 5 seconds with 16. That actually makes sense. It looks like up here they were doing half of it just for the fun of it. And then using a GPU, it's 0.18. Significant boost, right?
Mm-hmm.
Especially since your GPU will probably consume less power. So, what? So well, they went ahead and did some other timings just to run it. A CPU took, if a CPU on one of their timings took 20.5 seconds, non-optimized GPU was 0.15 and the optimized was 0.07. So in other words, there is a significant performance boost if you're able to leverage the GPU correctly. Hey, they gave us a picture.
It's so beautiful.
What's really going on here, this picture, I don't think gives you a good idea. This is memory, and this is a bunch of computation logic. This really does not help you. There's even more processing logic in here, is really what's coming down than over here. Most of the space taken up here is cache, and then like I/O controllers, data memory controllers, controllers, and then maybe in the middle you have your 4 processors right there. Over here you got processors, streaming processing units everywhere. The point is that the GPU has a lot of processing elements to it, or a lot of ALUs, while the CPU has to be general purpose, so it has to take care of a bunch of other overhead. Let's see, bus. The one on the left is a GPU card. The one on the right is a CPU. I think that's a Xeon, yeah, Intel Xeon. Wider bus. Notice that it has less memory, but the bandwidth is higher. The cache is smaller, but the number of cores is greater. Yeah, you remember that card, right? Nope. What are they up to? 1080?
1080, yeah.
Yeah, 1080 right now? Okay. Well, even then, back then. And how many cores are on that thing?
It's like, what, 8 years ago?
No, how many cores are on the
Oh, yeah.
1080?
2000 maybe?
2000?
I don't know.
Oh, look it up. 2, no. Good try.
1080.
Even 1080 Ti now.
Yeah.
More
So the
than
takeaway here, there's a lot more processing power. There's less memory, but more throughput with the memory. So it's able to crunch through numbers faster, but it's not able to hold as much. So hopefully you understand why this is important, because in certain applications, the GPU, can significantly boost the performance of your application.
There's 2,560 cores.
That makes sense. 2,560 cores, right. All right. So hopefully I've explained why OpenCL is useful. For certain applications, it can be a tremendous boost. Yes, David?
The TI has 3,500.
Oh, okay, 3,500. They just keep adding more, don't they?
Yeah, there's 1,000 more.
Why not? We'll
Does
just.
that mean they make the size bigger, or then the processor gets smaller?
Well, remember we're going back to our fabrication technology. When the transistor gets smaller, that means you can put more cores on the same area. But if you're not able to shrink the transistor, then your area just becomes bigger.
I mean, my 1080 is a foot long.
Well, also that's your card.
Yeah.
Your chip is
So-
only a
so
part of it. You'd have to take off your heatsink to find it, which don't do that.
Do it? Okay.
Don't
Yeah.
unless you're doing liquid cooling.
I wish.
That is nice.
Then you gotta use your own strips. You gotta put this, you know what I mean?
Yeah,
That
that is. By the way, that's very nice. I had that set up once.
But I don't.
At
What,
work.
what about? Is that kind of dangerous? I mean, like, what about
Not really.
leaks and stuff?
I had one that ran for 4 years. And it was,
Like your own, your custom own.
Yeah. Like you bend the tubing on it.
It's so quiet. Everything runs cool. It's
No
great.
fans.
Yeah, but definitely costs more. Anyways, why are we using OpenCL? Well,
because we want to.
Well, the word is open. The point here is you have different cards. You might have NVIDIA or ATI, or I'm sorry, AMD now. AMD.
ATI. Is that their previous thing?
ATI, it used to be NVIDIA versus ATI. AMD bought ATI. So AMD. And you used to, well, also Matrox used to have a couple, and there were other companies as well. But the point is you have two big competing ones. You'd like to have a language that worked on both of them. So OpenCL is just a language to help you run code through these GPUs that can run on either AMD's or NVIDIA's one, and really just anyone else that decides to implement the standard. Being open means that it's available to everyone. So if you wanted to design your own graphics card and make it OpenCL compliant, you could, if you wanted to. Notice that it's implemented by hardware vendors. So any piece of hardware that is OpenCL compliant, many graphics cards are. Most of your CPUs are as well if you wish to run your OpenCL code on your CPU, although that's not the intent, but you can if you need to. That's nice. They call it a clean API. All right. The idea is that it's standard, has good thread management. Okay, it uses all resources. It's IEEE compliant. So floating point. Y'all remember floating point? So it is actually compliant with floating point. And they try and give some guidelines to future designs that would make things easier for programmers.
We want to make things easier.
No. All right, so if you recall from the presentation, I told you need to tell me if your technology is coarse grain or fine grain. Let me explain to you what that is. Coarse grain is essentially how big of a computing unit you're using, while fine grain is how small, I guess, or how fine it is. So with grid computing, you're using separate machines to do all your computations. So remember, SIMD and vector machines, you have one instruction and multiple little programming elements inside of the core that you're using. And then you have things in between. You might have threads, that'd be a little more coarse grain, but still more on the fine grain side. Excuse me. MPI, you wouldn't, on a grid, you're going out through the whole internet. On MPI, you usually have a local cluster of machines. So that's still very coarse grain, but not as coarse as a grid. So where does GPU kind of fall into that? Well, the GPU uses a very wide SIMD and vector machines, but you also have multiple threads executing at the same time. So it's somewhere in here on the fine grain side of things. Did that make sense? Because y'all will be asked that question again. If you're executing separate processes, you're a coarse grain. If you're doing threads or below, like data parallelism, it's going to be fine grain. The split's basically right here. I cover up OpenMP because OpenMP can sometimes bleed into coarse grain. But hopefully none of y'all will have that issue. All right. What's the idea? Okay, the idea is, I think this example really helps you out. You really are removing one level of loops. So you're going to execute all the iterations of a loop in parallel is the idea. So instead of going from I to N to do something, and you just keep looping over and over and over again, you find the idea and then you just run it on your GPU. And what that does is it literally forks all these, forks a thread or creates a thread to execute this code on all the different streaming processing elements in parallel and then give you the result. Hopefully y'all can see why that's advantageous, because now you don't have to do branch prediction, which caused a lot of issues in your pipelining. You set up the data, you push it through, and then you get it back. That's really what it comes down to. So let's see. For your grid, what do we got here? For each grid point P, for each atom A, you compute the distance and update the field. Do they not explain this? All right. This is where you can skip a bit, and that's okay. There we go. Yes?
So how soon after processors did graphic cards come out?
Let's see, graphics cards, well, you've always had a frame buffer. So you've always had to have one somewhere. So having a graphics element of some sort always had to exist. But when did you have a separate card? Ooh, I do not remember. But you're probably asking, when did graphics cards become popular for gaming? I would look up Voodoo, and that's probably the Voodoo graphics card, from what I recall, is one of the very first ones that was extremely popular. There were probably some earlier ones, but if I were to guess which one made it popular, it'd be that one. So that's probably, my guess is early 90s?
Yeah.
Early 90s, yeah. Because before then, what people did is they would have to write assembly that would run on your processor in order to be as efficient as possible with your frame buffer that the machine was using. And so they're really happy when that came out because you didn't have to write assembly anymore. What year was that card come out?
This one says 1994.
94?
That's running through the FX. Yeah.
Does it have a predecessor?
Voodoo graphics card towards the end of 1996.
Usually it says predecessor over here. No predecessor? It has successor, but no predecessor.
So then,
So, okay. All right. That makes sense. Yeah, 94. That's about right. Okay. Can GPUs help with everything?
No.
No. Okay, good. Thank you, Jonah.
You're welcome.
Making sure you're paying attention.
Yep.
Some things, what?
It depends.
It depends. Some things it helps very well. Other things are absolutely terrible with. Really, anything that's in the quote is embarrassingly parallel, where you can execute all the iterations of a loop in parallel, is great. If we're going to go back to this example, if the next iteration of the loop depended on the answer of the previous one, you could not use the GPU to help you out because you need to execute each individual part of the loop in series. So a GPU wouldn't be helpful there. Like if you had f of a of I, comma b of I, comma c of I minus 1, then that would not be very helpful because you have a data dependency with the previous iteration of the loop. But in things that don't have previous dependencies, the GPU actually works great for. So they listed some examples here. Random number generations, some sorting, I wouldn't say all, but most sorting. Regular language parsing is actually pretty good, which ends up being kind of leads into cryptography. Not so well anything sequential, like I said earlier. Any non-local calculations, so anything that has to be done on a separate device. If you have to communicate over the network, it's terrible for that. Anything that has a very specific device depends on it's not so good. So some things are good, some things are not. How do you program it? Right now you have C++ support and you also have C support. They added Fortran, so all you people that love Fortran, you're good to go.
Finally.
Python actually has had it for a while as well. And they basically just use libraries that you import into your program and then use them. So you have NVIDIA and AMD. Those are probably not surprising to y'all. Keep in mind that Intel still produces graphics chips for their embedded processors. So they have OpenCL bindings inside of them. IBM, I don't know if they still do it, but they have been supporting it in the past. And they've been slowly integrating these OpenCL libraries into different programs in MATLAB and Mathematica. Have y'all used those yet? Maple?
Yeah.
Maple, okay.
Garbage.
Yeah.
Yeah, to us, computer science is like, why
Maple
are we
is
doing
It
this?
is so bad. Everyone's
hate
like, oh, this
Maple.
must be what code's like. No.
Like, yeah, to programmers, you're like, please no. You're like, can we at least? I'll even after using that, I was like, I'll take Python right now.
Yep.
Yeah.
Yep. Yep.
That says a lot.
So yeah, MATLAB, Mathematica, Maple, they're all integrating OpenCL capabilities, data parallelism, some other tools as well. All right, you got more and more bindings, more debuggers. Actually, this is these tools have really started to integrate the GPU more and more as time moves on. And some of these tools will no longer run unless you have a graphics card to connect them to, even though you could just do it on the processor. If you remember Hashcat, has anyone used that one? Hashcat? Hashcat? Oh, that's a tool for running. That's a tool for trying to crack hash codes. So you pipe in the hash, the salt, what type it is, and then you give it a dictionary file, or you give it a little string of like it's some of these words with maybe like some numbers before or after, and it would try and guess what the correct answer is. And it's if you use the GPU, you get a speed of like 50 to 100 or something ridiculous. While it takes forever on your CPU. All right, y'all don't know any myths about the GPUs because y'all haven't had problems with them. I kind of disagree with this first one. Hard to program. You have to. It's a different programming model because you have to drop some of your ideas about, I guess, looping, and you have to also think in parallel, which, as you've probably experienced, is not the easiest thing to do.
Nope.
But it's not as bad as trying to do Verilog. It is actually accurate. These are myths, so some people think it's not accurate, but they are accurate nowadays. They used to not be, but nowadays they are. Possible future? Well, actually, we've seen the future. It's pretty much gone into
GPU.
Well, why are GPUs so expensive now?
Mine.
They're amazing.
Mining, yes. So people are using them to mine.
Mm-hmm.
Mm-hmm.
Cards just sell like $100 over retail.
My
Yeah.
card is double its value from when I bought it, so.
Have you tried to sell it?
No, I'm not going to.
I probably would.
Like, it's tempting, but I don't.
Yeah, I went like last month. I was like, maybe I'll buy a new PC. I haven't bought one in about 5-6 years.
Yeah.
Not gonna
Yeah,
happen.
I need to build a new one.
They pretty much say if you want to buy one right now, just do a pre-built because pre-builts aren't affected by the GPU prices.
Oh, okay.
So.
Really?
Yeah. Because they get it
I
from
need to
straight from
build
the
a
retail.
desktop.
So like their
Yeah, but
graphics cards, and they usually get them at a deal, like a discount.
Next
get like a
big
pre-
project is building a desktop.
But you get a pre-built, it's probably more expensive.
Yeah.
No, actually they equal out to be the same price now.
Really?
Yeah, they've gotten really good
Yeah.
about it.
Really?
Yeah.
Well, they've also gotten good about the kits or the packaging.
But usually they have like. cheaper
Anyway.
All right. All right, that's all for today. Any
Oh.
questions about OpenCL?
Nope. I have other questions.
No other questions? All right, that's it for today.
cases. All right.
I feel like I'm not testing something correctly.
Okay.
Probably not.
There's that F word again.